Hi everyone. In the last lecture, we have learned how to implement a simple money transfer transaction. However, we haven't updated the account balance yet because it's more complicated and require careful handling of concurrent transactions to avoid deadlock. So in this lecture, we're going to implement this feature to learn more about database locking and how to debug a deadlock situation. Today I'm going to use a different implementation approach, which is test-driven development or TDD. The idea is we write tests first to make our current code breaks. Then we gradually improve the code until the test passed. Okay, this is a test that we were working on in the previous video. It creates 5 Go routines to execute 5 concurrent transfer transactions, where each of them will transfer the same amount of money from account 1 to account 2. Then it iterates through the list of results to check the created transfer and entry objects. Now to finish this test, we need to check the output account and their balances. Let's start with the account. First, the from account, where money is going out. We check it should not be empty, and its ID should equal to account1.id. Similar for the to account, where money is going in. The account object should not be empty, and its ID should equal to account2.id. Next, we will check the account balance. We calculate the difference between the input account1.balance and the output from account.balance. This diff1 is the amount of money that's going out of account 1. Similarly, we calculate the difference between the output to account.balance and the input account2.balance. This diff2 is the amount of money that's going into account 2. If the transaction works correctly, then diff1 and diff2 should be the same, and they should be a positive number. Also, this difference should be divisible by the amount of money that moves in each transaction. The reason is, the balance of account 1 will be decreased by 1 times amount after the first transaction, then 2 times amount after the second transaction, 3 times amount after the third, and so on and so forth. Because of this, if we compute k equals to diff1 divided by amount, then k must be an integer between 1 and n, where n is the number of executed transactions. Moreover, k must be unique for each transaction, which means k should be 1 for the first transaction, 2 for the second, 3 for the third, and so on until k equals to n. In order to check this, we need to declare a new variable called existed of type map int bool. Then here we check that the existed map should not contain k. After that, we set existed k to true. Eventually, after the for loop, we should check the final updated balance of the two accounts. First, we get the updated account 1 from the database by calling testqueries.getAccount with the background context and the ID of account 1. This query should not return an error. We get the updated account 2 from the database in the same manner. Now, after n transactions, the updated balance of account 1 must decrease by n times amount. So we require the updated account 1.balance to equal to that value. We have an error here because of the mismatch type between n and amount. Amount is of type int64, so we need to convert n to int64 before doing the multiplication. Alright, now we can do the same for the updated account2.balance, except that its value should be increasing instead of decreasing. And that's it, we're done with the test. But before running it, I'm gonna write some logs to see the result more clearly. First, let's print out the balance of the account before the transactions. Then print out the updated balance after all the transactions are executed. I also want to see the result balance after each transaction, so let's add a log here as well. Alright, we can now run the test. It fails at line 83, where we expect the from account to be not empty. But of course it is empty at the moment because we haven't implemented the feature yet. So let's go back to the store.go file to implement it. One easy and intuitive way to change the account balance is to first get that account from the database, then add or subtract some amount of money from its balance, and update it back to the database. However, this is often done incorrectly without a proper locking mechanism. I'm going to show you how. First, we call queue.getAccount to get the from accounts record and assign it to account1 variable. If error is not nil, we return it. Else, we call queue.updateAccount to update this account balance. The ID should be argument.fromAccountID, and the balance will be changed to account1.balance minus argument.amount. The updated account record will be saved to result.fromAccount. And if we get an error, just return it. After this, we have moved money out of the from account. Now we can do similar thing to move those money into the to account. I'm just copy this block of code, then change this variable to account2. This one to argument.toAccountID. The result will be stored in result.toAccount. This account ID should be argument.toAccountID. And the new balance should be account2.balance plus arguments.amount. Okay, so the implementation is done. However, I'm telling you it's incorrect. Let's rerun our test to see how it goes. The test still fails, but this time the error is on line 94, where we compare the amount of money that goes out of account 1 with those that goes into account 2. In the log, we can see that the first transaction is correct. The balance of account 1 decreases by 10 from 380 to 370. And the balance of account 2 also increases by 10 from 390 to 400. But it doesn't work correctly in the second transaction. The balance of account 2 increases by 10 more, while the balance of account 1 stays the same. To understand why, let's look at the getAccount query. It's just a normal select, so it doesn't block other transactions from reading the same account record. Therefore, two concurrent transactions can get the same value of account 1 with the original balance of 380. So it explains why both of them have the updated balance of 370 after execution. To demonstrate this scenario, let's start the PSQL console in two different terminal tabs and run two parallel transactions. First, I will begin the first transaction in this tab, then switch to other tab and start the second transaction. In this transaction, let's run a normal select query to get the account record with ID 1. This account has a balance of 748 euro. Now I'm going to copy this query and run it in the other transaction. As you can see, the same account record is returned immediately without being blocked. This is not what we want. So let's roll back both transactions and learn how to fix it. I will start two new transactions. But this time, we will add forUpdate clause at the end of the select statement. Now the first transaction still gets the record immediately. But when we run this query on the second transaction, it is blocked and has to wait for the first transaction to commit or roll back. Let's go back to that transaction and update the account balance to 500. After this update, the second transaction is still blocked. However, as soon as we commit the first transaction, we can see that the second transaction is unblocked right away, and it gets the newly updated account with balance of 500 euro. That's exactly what we want to achieve. So let's go back to the account.sql file and add a new query to get account for update. I will just copy this get account query and add for update at the end. Then we open the terminal and run make SQL to regenerate the code. Okay, now in the account.sql.go file, a new get account for update function is generated. We can use it in our money transfer transaction. Here, to get the first account, we call queue.getAccount for update. We do the same thing to get the second account. Alright, now we expect this to work. Let's rerun our test. Unfortunately, it still fails. This time, the error is deadlock detected. So what can we do? Don't worry, I'm going to show you how to debug this deadlock situation. In order to figure out why deadlock occurred, we need to print out some logs to see which transaction is calling which query and in which order. For that, we have to assign a name for each transaction and pass it into the transfer_tx function via the context argument. Now inside this for loop, I'm going to create a txName variable to store the name of the transaction. We use the fmt.sprintf command and the counter I to create different names, tx1, tx2, tx3, and so on. Then inside this go routine, instead of passing in the background context, we will pass in the new context with the transaction name. To add the transaction name to the context, we call context.withValue. Pass in the background context as the parent context and a pair of key value, where value is the transaction name. Here says the key should not be of type string or any built-in type to avoid collisions between packages. Normally, we should define a variable of type struct for the context key. I'm going to do that in the store.go file, because later we will have to use this key to get the transaction name from the input context of the transfer_tx function. Here we declare a variable tx key of type empty struct. The second bracket means that we are creating a new empty object of that type. Alright, now let's go back to the store test.go file and pass the tx key and tx name to this function. After this step, the context will hold the transaction name, and we can get it back in the transfer_tx function by calling ctx.value to get the value of the tx key from the context. Now we have the transaction name. We can write some logs with it. Let's print out this transaction name and the first operation, create transfer. Then let's do the same for the rest of the operations. This operation is to create entry 1. This one is to create entry 2. This operation is to get account 1 for update. This one is to update account 1's balance. The next operation is to get account 2 for update. And the last operation is to update account 2's balance. Alright, now we can rerun the test to see how it goes. But to make it easier to debug, we should not run too many concurrent transactions. So I'm going to change this n to 2 instead of 5. Then let's run the test. And voila, we still get the deadlock. But this time we have detailed logs of what happened. As you can see here, transaction 2 ran its first two operations, create transfer and create entry 1. Then transaction 1 jumped in to run its create transfer operation. Transaction 2 came back and continued running its next two operations, create entry 2 and get account 1. Finally, the transaction 1 took turn and ran its next four operations, create entry 1, create entry 2, get account 1, and update account 1. At this point, we got a deadlock. So now we know exactly what happened. What we have to do is to find out the reason why it happened. Here I have opened the Simple Bank database in Table Plus, and at the moment, it has two accounts with the same original balance of 100 USD. I also prepared the money transfer transaction with a list of SQL queries that should be run exactly as we implemented in our Golang code. The transaction starts with a begin statement. First, we insert a new transfer record from account 1 to account 2 with amount 10. Then we insert a new entry record for account 1 with amount of minus 10, and insert another entry record for account 2 with amount of 10. Next, we select account 1 for update, and we update its balance to 100 minus 10, which is 90 USD. Similarly, we select account 2 for update, and we update its balance to 100 plus 10, which equals to 110 USD. Finally, we do a rollback when deadlock occurs. Now, just like what we did before, I'm going to open the terminal and run 2 PSQL console in order to execute 2 transactions in parallel. Let's start the first transaction with begin. Then open another tab and access the PSQL console. Start the second transaction with begin. Okay, as we've seen in the logs, first transaction 2 must create transfer and entry 1. So let's copy this insert query and paste it to this transaction. The transfer record is created. Next, the query to create entry for account 1. Inserted successfully. Now we have to move to transaction 1 and run the first query to create transfer record. Now back to transaction 2 and run its third operation to create entry for account 2. Also successful. Then the fourth query to get account 1 for update. Now we see that this query is blocked. It is waiting for transaction 2 to commit or roll back before continue. It sounds strange because transaction 2 already creates a record in transfers table while we are getting a record from account table. Why an insert into one table can block a select from other table? To confirm this, let's open the browser and search for PSQL log. This long and complex query allows us to look for blocked queries and what is blocking them. So let's copy and run it in Table Plus. As you can see, the blocked statement is select from account for update, and the one that's blocking it is insert into transfers. So it's true that queries on these two different tables can block each other. Let's dig deeper to understand why the select query has to wait for the insert query. If we go back to the Postgres wiki page and scroll down a bit, we will see another query that will allow us to list all the logs in our database. Let's copy it to Table Plus. I'm going to modify this query a bit because I want to see more information. This a.dat_name field will show us the database name. Let's add a.application name to see which application the log comes from. The l.relation red class is actually the name of the table. The l.transaction ID is the transaction ID. l.mode is the mode of the log. Let's also add l.log type to see the type of the log. l.granted tells us whether the log has been granted or not. a.username is the username who ran the query. a.query is a query that's holding or trying to acquire the log. The time when that query started or its age are not very important, so I'm going to remove them. The last field is a.pid, which is the process ID. As you can see, we're selecting from the PG state activity table, alias SA, and join with the PG logs table, alias SL, on the process ID column. It is ordering by the query start time, but actually I think order by process ID is better because we have two different processes that are running two PSQL consoles with two parallel transactions, so it will be easier to see which log belongs to which transaction. Alright, let's run it. Here we can see some logs from Table Plus application which are not relevant. What we care about is only the logs that came from PSQL consoles. So I'm gonna add a where clause here to get only the logs with application name equals PSQL. The database name is also not important because it's always simple bank in our case. So I will remove a.datName as well. Okay, let's run this query again. Now we can see there is only one log that hasn't been granted yet. It comes from the select from account query of the process ID 3053. The reason it's not granted is because it is trying to acquire a share log of type transaction ID, where the transaction ID is 2442, while this transaction ID log is being held exclusively by the other process ID 3047 with the insert into transfers query. But why a select from account table needs to get a log from other transaction that runs insert into transfers table? Well, if we look at the database schema, we can see that the only connection between account and transfers table is a foreign key constraint. The from account ID and to account ID columns of transfers table are referencing the ID column of account table. So any update on the account ID will affect this foreign key constraint. That's why when we select an account for update, it needs to acquire log to prevent conflict and ensure the consistency of the data. Having said that, now if we continue running the rest of the queries on transaction 1 to create entry record for account 1, create entry for account 2, and select account 1 for update, we will get a deadlock because this query also has to wait for a log from transaction 2, while transaction 2 is also waiting for a log from this transaction 1. And that clearly explains how the deadlock happens. But how to fix it? Okay, let me roll back these two transactions first. As we know, the deadlock is caused by foreign key constraint. So one simple way to avoid it is to remove those constraints. Let's try comment out this statement. Then run make migrate down in the terminal to delete the database schema. And run make migrate up to create a new DB schema without foreign key constraint. Alright, now if we run the test again, it will pass because the constraints are gone, so no log is required when select accounts for update, and no log means no deadlock. However, it's not the best solution because we don't want to lose our nice constraints that keep our data consistent. So let's revert these changes. Run migrate down, then migrate up again to have those constraints back. Now the test will fail because of deadlock again. Let's learn a better way to fix this issue. As we already know, the transaction log is only required because Postgres worries that transaction 1 will update the account ID, which would affect the foreign key constraints of transfers table. However, if we look at the update account query, we can see that it only changes the account balance. The account ID will never be changed because it's the primary key of account table. So if we can tell Postgres that I'm selecting this account for update, but its primary key won't be touched, then Postgres will not need to acquire the transaction log, and thus no deadlock. Fortunately, it's super easy to do so. In this query, instead of just select for update, we just need to say more clearly, select for no key update. This will tell Postgres that we don't update the key or ID column of the account table. Now let's run make /c in the terminal to regenerate Golang code for this query. Okay, the code is updated. Let's run our test again. It passed. Excellent. So our debugging and fixing is done. Let's remove our debug code. Change this n back to 5. Remove this transaction name. No need to add value to this context anymore. Then remove all logs in the transfer tx function. And this tx key variable as well. Okay, let's run the test again. It passed, and we can look at how the balance of the two accounts are changing after each transaction. The balance of account 1 is decreasing by 10, and the balance of account 2 is increasing by the same amount. Perfect. Now before we finish, I'm going to show you a much better way to implement this update balance operation. Currently, we have to perform 2 queries to get the account and update its balance. We can improve this by using only one single query to add some amount of money to the account balance directly. For that, I'm going to add a new SQL query called add account balance. It's similar to the update account query, except that here we set the balance equals to balance plus the second argument. Let's run make_SQL to generate the code. A new function is successfully added to the query struct. However, this balance parameter looks a bit confusing because we're just adding some amount of money to the balance, not changing the account balance to this value. So this parameter's name should be amount instead. Can we tell SQL to do that for us? Yes, we can. In this SQL query, instead of $2, we can say SQL.argument amount. And here, instead of $1, we should say SQL.argument ID. This amount and ID will be the name of the generated parameters. Okay, let's run make_SQL in the terminal to regenerate the code. This time we can see the parameters name have changed to what we want. Cool. Now come back to the store.go file. I'm going to remove this getAccount for update call and change this update account to add account balance. This should be add account balance params. Change this balance field to amount and remove this account under balance. Let's do the same thing for account 2. Remove this getAccount for update. Change this to add account balance. This one to add account balance params. This balance should be changed to amount. And remove account2.balance here. And we're done. Let's rerun the test. Oops, it fails. The error is on line 95, where we compare the diff. Expected -10, but actually got 10 instead. Okay, I know why. Here when we update the balance of the from account, the amount should be minus argument.amount because money is moving out. Alright, now this should work. Let's rerun the test one more time. Yay, it passed. Let's run the whole package test. All passed. And that's it for today's lecture about locking in DB transaction and how to debug a deadlock. I hope you enjoy it. And stay tuned for the next lecture, because I'm telling you, the deadlock issue is not completely resolved yet. There's much more to learn about it. In the meantime, happy coding and I'll see you very soon.